Digital DJ, play us in. Today my partners Cannon and Prithvi and I will be discussing deep neural networks for music generation. I will be talking about the introduction, motivation, as well as the related work. Cannon will be going through the pre-processing steps and the model layers in music generation. Prithvi will be talking about experiments and model output strategies and results, and then Cannon will finish up with the conclusions. The goal of our project is to reproduce some of the key components found in music. In addition, we are avid music listeners, so this project is a little personal to us. Some known challenges of producing music with a neural network are lack of musical rhythm, structure, and melody. There have been research projects done on this topic before. One common model involves residual neural networks. These have the downfall of vanishing gradients, but LSTM can produce global structure and local structure, which solves that problem. And then ResRNN attempts to solve the vanishing gradient problem, but we decide not to use that. Next, long short-term memory demonstrates neural networks can generate music, but networks might not be big enough to avoid false notes and imperfect melodies.
Now I'll discuss a little bit of the data pre-processing stages. So initially what we were looking for in our data was something that we could break down to be the input of our model. And because of this, MIDI files ended up being the exact thing we needed. Using a MIDI library of primarily drum beats that was collected by the Reddit user MIDIman, we parse these down into their basic components of notes and rests and chords. And then from this, we, just like a natural language processing network, we cast all of these to a vocabulary list and then cast all of those values to integers to be fed into our model. So our model consisted of 5 different layers, and this was the end result after a good amount of experimentation and looking at the things that were outcoming from our previous models. So we started off with the embedding layer, and this is where we inputted our 1,200 different notes into the model to have the dimensions reduced. Then we moved on to the LSTM network, which allowed us to access some of the data from the previous predictions and then use it in this prediction, followed by a dropout layer, and then an additional LSTM layer followed by the output of a linear layer. We decided to go with 2 LSTM layers with the dropout in between because it allowed us the flexibility to have good model predictions, but the dropout allowed us to have the robustness to predict notes and not overfit on the training set. So the final step was generating the music from the model that we had trained. So what we did was we started each output sequence with our most frequent starting note of all the audio clips that we had. So this gave us a head start because the model had been trained the most on these specific instances of starting notes. Then, with each progressive feed into the model, we slowly built the song until we had 500 subsequent notes to create into our final melody. Then, using prediction probabilities, we prevented degeneration into the same note sequence. This meant that instead of taking the max, the note that was most likely to happen next, we allowed the logits to predict based off of the multinomial distribution.
Alright, so let's go on to our experiments. We experimented with multiple models throughout our process. So when we were first starting, we started with the RNN with LSTM layers, which is one of the main structures used for this type of sequence modeling. And we actually started with one hidden layer with 128 nodes, a learning rate of 0.001. And for all the models, we used the Atom Optimizer because it's commonly used, and cross entropy loss. But the validation accuracy of this model was not great. It was around 8.96%. So we knew we had to make a few tweaks. So we experimented with other models. So our second model was also an RNN with LSTM layers. We actually added 2 hidden layers for this model, and each one had 32 nodes within it. So there's more hidden layers, but there's less nodes within each layer. And then we also kept the same learning rate of 0.01. And we also added a 90% dropout to prevent overfitting with the same loss and optimizer functions. So actually the addition of the hidden layers actually increased our validation accuracy to 17.02%. And then for Model 3, we did the same thing as Model 2, but we decreased our learning rate to 0.0005. This actually made a significant jump in validation accuracy to 38%, and the accuracy is actually measuring whether or not, given a note in a song, we get the next note right. So that's something I thought I would just clarify. So obviously, accuracy, it's important to see for our model to make sure that our model is performing well, but what we were mostly concerned with was what our actual generated music looked like. So when we first started off with the softmax output layer, and we were trying to pick the next note with the highest probability generated from this output layer, so the maximum probability. But what ended up happening is there was little distinction between the notes. There was like 2 or 3 notes being played over and over again, and we were actually trying to produce actual music with a beat and melody, and this was not fulfilling that criteria. So then after that, we did some research. We found that you can actually select a random sample from these probability distributions generated from the softmax layer. So by introducing some randomness, we were able to get a wider variety of notes, and this actually ended up resulting in 105 distinct notes for a song of length 500. So after that, we dug even more into this notion of randomness into our outputs, and we introduced a temperature measure. So what the temperature measure does is it scales the logits before calculating the probits, and through this we were able to control the randomness. So the higher the temperature, the higher the randomness, and the temperature of 5 actually resulted in around 400 distinct notes. So yeah, as I was talking about before, these are some of the note distributions. So our first one to the left is the softmax layer outputs, and as you can see, there's only 3 distinct notes. And then for the next 2, the first one is the middle one is a random multinomial note distribution, and for that one, there's actually 105 distinct notes, but I've only showed the top 10 on this graph. And same for the temperature one, there's actually 400 distinct notes, but I've only showed the top 10. So as the randomness increases, we get a wider variety of notes. So with our results, we ended up with our final model was the RNN with LSTM layers, 2 hidden layers with 32 nodes, 0.005, 90% dropout, atom and cross entropy loss, and we actually ended up training it over 50 epochs. Then our final output strategy is actually just sampling from the multinomial distribution created from our probabilities from the softmax layer. And we ended up just setting the temperature to 1, so we could still depend on these probabilities, but also not have notes repeating over and over again. And I actually have Canon right now play an example output with some starting note.
And then that'll play us into our conclusion. So some of our findings were that it is possible to produce music with a beat and a pattern. One of the things that we noticed often while looking at the different arrays of notes that we were seeing was that very often there were rest gaps in between each note, indicating that the algorithm did pick up on the spacing of these notes as they were played out through the MIDI file. Some future implications that we'd like to look at: now that we know that it is possible to replicate this beat and pattern, we'd love to experiment with different note types, things from different instruments such as orchestra music or like actual guitars playing, and then find out how to accurately predict pitch types as well as this continuous beat and pattern. So now I would like to have Digital DJ play us out.